Hello everyone, I'm Aastik Sharma. I'm also a part of Pollution Prevention Group at West Virginia University, and today I'll be talking about the compressed air system. It is a vital part of our industrial system, so we'll discuss the practical ways to make this system more efficient, reliable, and sustainable, and how those improvements can reduce both cost and environmental impacts. Here is a quick look at what we will be covering today. We'll start off by understanding what a compressed air system is and go over its main components. Then we will look at the different type of compressors and how they operate. Next, we will explore some of the common efficiency loss, things like leak and pressure drop that can really impact performance. After that, we will highlight some energy saving opportunities on the compressed air system. Before we jump into the discussion about the compressed air system, let's look what we mean about the industrial system. So as discussed in previous presentation, the industrial system includes lighting, HVAC, boilers, motors, fans, compressed air, building envelope, and steam system. Uh, This system, along with the equipment specific to their processes, represent all or most of the energy used in the typical industrial facility. Each of these systems significantly influence the overall energy efficiency and energy cost of the facility. So today we will be focusing on compressed air system. Let's begin with the fundamental of how it operates. A compressor is essentially a mechanical device that increases the pressure and reduces the volume of a gas. Electric motors are used to compress air. That pressurized air is then distributed through the system to power tools, equipment, or different industrial processes. The compressed air system can be broadly divided into a supply side and demand side as shown in the slide. On the supply side, we start with the compressor which generates compressed air, the air that goes into a wet storage tank, which helps smooth out pressure fluctuations and also allows some of the moisture to settle down. Next, the air passes through a dryer, which removes excess air moisture to prevent problem in the equipment and processes. After that, it is stored again in a dry storage tank before being sent out for the use. So on the demand side, the compressed air is distributed to different end users and processes, which could be tool, actuator, or machinery that depend on a steady supply of clean, dry, and pressurized air. Compressed air is often called the fourth utility, right alongside electricity, water, and natural gas, because it is so widely used in the industry. The compressed air is used in different industries for packaging, even cleaning, powering tools, stamping and painting processes. It supports conveying, mixing, and sterile process control. It is also used in forming and shaping materials. It plays roles in material handling, HVAC systems, air brakes, and even energy storage. Across this sector, compressed air is truly a versatile energy source, but it also comes with a high energy cost if not managed efficiently. So let's focus on the different type of compressors. Compressors are generally classified into two main categories: positive displacement and dynamic. The positive displacement compressor work by trapping a fixed amount of air and squeezing it through a smaller volume to raise the pressure. Single stage, double stage, and screw type compressor comes under positive displacement compressor. Dynamic compressor, on the other hand, use speed instead of volume reduction. They accelerate air to a high velocity and then convert that velocity into pressure. The main type of centrifugal compressor is Um, the main type of dynamic compressor is a centrifugal compressor, which use a spinning impeller, and axial flow compressor, which compresses air through a multiple rows of blades. So the compressor can be classified depending on its use. Small capacity, a single stage reciprocating compressors are most common. Industry use them where the air demand is low or irregular. In a medium capacity range, rotary screw compressors are popular in manufacturing plants because it strikes the right balance. It can deliver high pressure and steady airflow without the massive investment of larger system. At the large capacity industries to turn industry turn to centrifugal and axial flow compressors. They are built for scale like refineries, chemical plant, and large automotive facilities. So after looking at the different type and capacities of the compressor, the big question is why should we even care about the compressed air system? Compressed air is one of the least efficient form of energy. Up to 85% of the energy put into the compressed air is lost as heat. That means only 15% makes it to a useful compressed air. Let's look at the cost breakdown on the right side of the slide. Over the lifetime of the compressed air, 76% of the cost is just electricity to run it. Equipments and maintenance combined make up less than a quarter. So when we think about the compressed air, the real opportunity isn't in buying cheaper equipments. It is managing energy use and reducing waste. That is where the saving and the sustainability gains truly come from. We are going to look into the possible potential areas of improvement that can deliver big savings in compressors. So this slide here is really showing us a roadmap for both upstream at the compressor and downstream at the point of use. There are opportunities to cut cost, save energy, and make the system work smarter. On the supply side, improvement can come from optimizing the compressor itself, improving intake and treatment, upgrading controls, or even adding proper storage. Addressing leaks and pressure drop here is critical since even small inefficiencies quickly multiply into large energy losses. And let's not forget about heat recovery, which is often overlooked, but it can capture a large waste heat and put it to a good use elsewhere in the facility. On the demand side, it is about how the air is being used. Are there leaks in the distribution system? Are we using compressed air for the job that could be done more efficiently other way? Even something as simple as switching to efficient nozzle can lead to a real saving. Let's discuss about the major energy saving opportunities in the compressor. The first one is the repairing compressed air system leaks. Leaks are always there. Every system has them, and they are often responsible for wasting 20 to 30% of the total compressed air. That is a huge hidden cost, and also provide a quick win after repairing those leaks. What makes leaks so important is that the payback period is very short. Simply repairing them can deliver immediate saving without requiring major investments. Most leaks occur in common spots like coupling, hoses, fittings, pressure regulators, pipe joints, and filters. Here is the powerful part. Eliminating just 10 leaks, each only about a quarter inch in size, can account for nearly 70% of the overall saving potentials. So fixing leaks isn't just maintenance, it is one of the fastest and most effective strategy for improving system efficiency. There are three good ways to identify leaks. One of the simplest and most effective method is to routinely walk the system and listen for the hissing noises. You would be surprised how often leaks goes undetected until someone takes the time to listen carefully. Of course, in a noisy industrial environment, our ear aren't always enough. That's where ultrasonic probes comes in. These tools can pick up high frequency sounds from even the smallest leak helping maintenance team locate issues and quickly and accurately repair them. After identifying leaks, the next step is tagging and tracking them. This may sound simple, but it is one of the most effective way to stay organized. By marking leaks with visible tags, like you see in the images, maintenance team can easily identify where issues are and track which one have been repaired. So far, we have looked at spotting leaks with inspection and tagging them for follow-up. But what if we want to measure the overall impact of the leak in our system? That is where the bleed down test comes in. Think of it like a health checkup of your compressed air system. Here is how it works. With the plant shut down, we need to pressurize the system to normal operating pressure, then simply monitor how quickly the pressure drops over the time. This gives a direct estimate of your total leak rate. It is a powerful diagnostic tool because it tells about just how big the problem really is. If your leak is under 5% of the demand, that is generally accepted. But once you hit 10% or more, it is a red flag. It tells that the system is bleeding energy and money. Next, we have system pressure reduction. After leaks, another big culprit is compressed air waste is pressure drop. Think of it this like compressor works hard to deliver air at a certain pressure, but by the time it reaches the point of use, a lot of energy may be gone, and the system compensates by running harder, which drives the energy use. Pressure drops often comes from things like undersized or restricted components, dirty filters or dryers, or simply poor piping design. Even a small restriction can add up to big losses across the entire system. Detecting this issue isn't complicated. It can be as simple as measuring pressures at different points, installing gauges across dryers, or using a data logger to see how pressure changes over time. Comparing those readings with manufacturing specifications helps pinpoint where the system is underperforming. So now that we have looked at the main causes of pressure drop, let's talk about how we can actually reduce it. One of the simplest and most effective strategy is adding secondary storage, or what we call a process receiver. Instead of compressor working overtime to keep up with the sudden burst of demand, the process receiver acts like a buffer. It stores compressed air at a stable pressure and releases it when needed, which keeps the system from dropping below the required operating pressure. Another simple way to cut down on pressure drop is by looking at how the system is laid out. If your system is designed in a straight line or linear setup, the air has to travel farther, and by the time it reaches the last end use, the pressure can be much lower. That is wasted energy, and it often pushes operator to crank up the compressor pressure just to compensate. A loop piping design solves this problem. Continuing with the pressure reduction strategy, one thing to watch out for is called collision connection. So we can see in the slide. This happens when two air systems meet hands-on in the piping system. The collision creates turbulence, pressure losses, and energy waste. A better approach is to design smoother junctions so air flow more efficiently into the pipe. The other bigger opportunity is the system pressure itself. A lot of plants run their compressor at higher pressure than they really needed, just to play it safe. But here is the thing: every 2 psi reduction in the pressure can save about 1% of the energy cost for the compressor, and across an entire facility, that adds up fast. Let's move to another smart energy saving opportunity using outside air for compressor intake. Cooler air is denser. When compressor pulls in cooler air, outside cooler outside air instead of warm indoor air, it takes less energy to compress it to the same pressure. It can reduce energy compression consumption by 3 to 5% for every 10-degree reduction in intake air temperature. This might not sound like much, but across thousands of operating hours, it adds up to the major energy saving. Let's talk about one of the simplest but often overlooked opportunity, eliminating inappropriate usage of compressed air. As you can see from this cartoon, the temptation to use compressed air in the wrong way has always been there. Someone is hot and sweaty on the job, so they grab a hose for a quick cool down. It might feel refreshing, but it is actually a really dangerous and wasteful practice. Compressed air isn't just expensive, it can cause serious injury if misused. The same goes for using it to sweep the floor or clean clothes. These are inappropriate uses that drain the system, waste energy, and put worker at risk. What this tells us is that saving energy with compressed air isn't just about technology, it is about changing behavior, educating staff, and creating simple rules around safe and appropriate use can go a long way toward improving both efficiency and safety. Now, let's look at some practical alternatives instead of compressed air used. So, instead of open blowing for cleaning, we can use brushes, brooms, or even low pressure blowers for sparaging and atomizing. Low pressure blower again work much more efficiently. And personal cooling, which people often do with compressed air, should really be replaced with something as simple as electric fans. We can also see cases where compressed air pump or equipment are left running even when they are not needed. That is like leaving the lights on 24/7. A simple fix is to install air stop valves or disconnect supply lines when equipment is idle. The other opportunity is designing a storage tank and sizing the storage tank size and the location of the storage tank. So storage tank plays a big role in system efficiency. If the tank is too small, pressure swings and the compressor will cycle on and off more often, wasting the energy. A larger, properly sized tank smooths out those fluctuations and give you steady air supply. Placement is just as important to keeping tank closer to where the air is used uh, as it stabilize pressure at the right point of the demand. So the right size and the right location means lower energy use, less wear on equipment, and more reliable performance. Now let's move on to waste heat recovery from the compressed air system. Almost all of the energy that goes into the running a compressor eventually becomes heat. We are talking about 90 to 95%. And in most facility, that heat just get dumped into the atmosphere and wasted. But instead of letting that energy disappear, we can capture it and use it productively. If you look at this diagram, it really tells the story of where all the energy goes in the compressed air system. On the left, we see 100% of the electrical energy going into the compressor. Only a very small fraction of that ever makes it into the useful compressed air. The majority is released as heat. Now some of that heat is lost immediately through radiation. Another chunk goes into the oil cooler and intercooler. That is where the real opportunity lies. Instead of just letting that hot air escape, we can capture it through direct heat recovery and condensation heat. Here are the major applications where waste heat can actually be put to good use. First, it can be used for heating. For example, keeping workspace, storage area, or even offices warm during cooler months. Second, hot water. Many facilities need large amount of hot water for cleaning or sanitation, and waste heat can cover a big portion of that. Third, it can support industrial processes, things like drying, curing, or preheating material. Instead of using extra fuel or energy, we can tap into recovered heat. And fourth is the ambient air heating. That means using the recovered heat to preheat incoming air, which is especially valuable in colder regions. Lastly, one simple change that can make a big difference in efficiency and equipment life is switching to synthetic lubricants. So finally, let's talk about the use of synthetic lubricants. What makes them stand out is how much more efficient they are compared to the conventional oils. For one, they reduce friction better, which means less energy wasted and high overall efficiency. Over the time, that also makes them more cost effective since equipment run smoother and last longer. They are especially useful in a high load operation where regular lubricant might break down. Plus, they are more stable in variable environment where it is really hot or really cold. They will still perform well. And one of often overlooked benefit is safety. Synthetic lubricants are less flammable, so they are safer in fire hazard areas. We explored the major opportunities to energy saving, repairing leaks, lowering system pressure, using cooler outside air for intake, eliminating inappropriate uses, sizing and locating storage tank properly, recovering waste heat, and even switching to synthetic lubricants. Each of these strategies may seem small on its own, but together they add up to a real efficiency gains, cost savings, and a more sustainable operation. So these are the references from which the com- compressor presentation slides are made. Thank you for your attention. If you have any questions or would like to discuss any part more in detail, I'll be happy to answer. Please provide me feedback using this QR code.